So good morning everyone. So we're going to have a look at this. It's one of the questions on the assignments, and it's about, we've got a load, 20 tonnes, and it's being pulled up a slope, which is a 1 in 5. So it goes up 1 every 5. So we need to work out what the angle is. If we find this angle here, that will also give us, that will be ideal for finding our other angles. So the weight's pulling it this way, but the normal is going to be that way. So that angle there will be ideal for doing the calculations, resolving the forces basically of the weight and the normal, etc. Okay. Remember the normal works perpendicular to the two surfaces that are pressed together. But this we've got to take into account for the weight that's going down the slope. And we're going to calculate how much effort it takes to pull that up against those resistances. We're told that it's 20 tonnes, it goes up 1 in 5. It starts at 0 speed-wise and accelerates to 18 kilometers per hour in 25 meters, and the friction coefficient is 0.75. If you remember, when something's on a slope, if it was a perfectly smooth slope, it just slides down straight away. So it's friction that stops it moving, which is exceptionally useful. So there's a couple of things we need to do first. One is work out what the angle is, what actually 1 in 5 means. So 1 in 5 is going to be, so we've got basically an old triangle, so it's 1 that way, 5 that way, and we need to know that angle, so it's just going to be an inverse of tan. So inverse of tan minus 1 over 1 over 5, and apparently that gives us 11.31. 11.31. So I'll put that on there. .31, that's useful, so I can, to save some space, I'll remove that. The other thing we need to find is the acceleration. So what we're going to use is we're going to use one of the so-called Servat formulas, you know, these standard formulas. We're going to use this one, v squared equals u squared plus 2as. So that's one of our first steps, is find out what the acceleration is before we even get to the questions. A couple of things to sort out, what the angle is and what the acceleration is. So if I rearrange that, I've got, there's another thing I need to do is work out, in fact I can't do this till I've done it actually, I need to convert 18 kilometers per hour into meters per second, so within SI units. So I'm just going to do that. So 18 will be times 1,000, so that gets into meters, because it is 18,000 meters, divide by seconds, so in per hour is 3,600 seconds, so that gives me 5 meters per second. So it's going 5, I'll put this up here, 5 meters per second.
What's that for, Kevin?
That's to, we're given that it's doing 18 kilometers per hour.
Right.
But to do things like this bit of maths here, for example, it's a lot easier to convert that into meters per second, use standard SI units.
Okay.
So 18 kilometers per hour equates to 5 meters per second.
How could you find this angle? By tangent?
Yes, I used the inverse of tan.
Can you just show us that formula? You rubbed it off.
Right, okay.
Tangent?
So it's inverse of tan, so it's opposite over adjacent, so it's 1 over 5. So if you put that in your calculator, in degrees, you get 11.31. Which feels right as well, because it's not going to be very steep, is it, if it's only gone up 1 when you've got along 5. Okay to rub that off?
Yeah, thank you.
Right, so now I've got my meters per second. So I'm now doing, so it's 5 squared, because it's doing 5, final velocity, V's final velocity. So it's 5 squared equals, initial velocity 0, so that's nice, plus, easier, 2as. And it does 25 meters, so let me put that in as well. In fact, let me put in there 50s. So 2 times 25 is 25 metres it travels, it tells us. So if I rearrange that, I'm going to get acceleration, sorry I've put the wrong letter in there, that should be A for acceleration. So A will equal 25 divided by 50. 25 comes from 5 squared, divide by 50, which gives me 0.5 metres per second, no, metres per second squared. So that's an acceleration. So I'll put that up there as well. So V equals that, A equals that, which is 0.5.
Sorry,
Point, right, 5 metres per second squared. I'll leave that on for a while. Okay, so we're about ready to go now. We've got mostly what we need. So first question there is draw force diagram. So force diagram. So remember we did this. So it's all the forces that that are acting on it, on our load. So we've got a load and it's being pulled by the effort this way, which we don't know what that is. You can calculate that. We don't know what this is, but this is the resistance, resistive force, or the tractive resistance is probably a better way of putting it, because these are all the forces acting on it, stopping it and going up the slope. So that's going to be resistance and the weight that it has to overcome. So these are all forces. We've got pulling down, we've got the weight. And the normal, I'm going to pull up this way, is at 90, perpendicular to the surface. So that's question A done straight away, nice and easy.
What diagram is that?
That's the force diagram, a nice simple neat force diagram. It's always good to do these to get an understanding of what's going on, so you know the different forces that are working on it.
Leave it on a second.
Yeah, sure. Yeah, at this point I'll leave things on as long as possible. So that's actually the answer to A. I'll leave this on acceleration formula for the while as well.
What did you use to draw that force diagram, Chris?
With pen? No, it's not what you mean, is it? Right, it represents all the forces that are acting on this load here, on this 20 tonnes. So you've got pulling down the resistance.
So that's just
yeah,
what you draw every time you do it. You've not used any.
Yeah, it's the tractive resistance is actually what it represents. It's what this needs to overcome to make it to cause it to accelerate.
Right.
To 0.5 metre per second squared. And then you've got the weight pulling down, gravity, in other words. Good old gravity. And then you've got the normal reaction, which is always perpendicular to your two surfaces that are pressing together. Okay. So that's A done. Question B. So this is find the normal reaction. So the N is simply, if you remember from before, is mg times cosine theta. So that's the how much force the normal is reacting to, the reaction to the weight on it really. Okay, so it's time cosine theta. It's this angle, this 11.31, because that's the same as that one in there. Okay, so that would give us, we've got mass is 20 tonnes, so that's 20 times 10 to the times 10 to the 3, 20 tonnes, megagrams, times gravity, which we're going to take as 9.8, nearly enough for this, times cosine, 11.31. And that gives us n equals 192,193.77. So that's fairly straightforward. Now C says find the frictional resistance, and if you remember the formula for this, is the frictional resistance is or mu times n. And we're given that mu is 0.75, so this is your resistance of your material. How rough it is, basically. And then ends the reaction. So that gives me 0.75 times our force, above force, at normal reaction. 192,193.77. That gives me 144, 145.33 newtons. Obviously, you can convert it to kilonewtons, but I'm going to leave it as newtons for now. Okay, so that's C done. So we're sailing through this. So D is the weight. So how much is it being pulled down the slope by the weight? So that's going to be, so the weight will equal mg. So mass times gravity is always gives you the weight in newtons. Remember, weight is not the mass as we think it is, as we're using general terminology, and it's times sine theta. So that again is our 10,000. In fact, I haven't even bothered writing it in, but I'll put it in. So that's our 10 tons, 20 tons, sorry. 20 tons times 9.8 times sine 11.31 gives me an answer of 384.99 newtons. Okay, so far?
What's that number after sine? 11.31.
3.1, yeah. Yeah, it's the sample here.
Yeah.
So E is the inertia resistance. So if you move anything along, you've got to overcome the inertia. And inertia takes, in this has got two parts. It's got the resistance of the friction, and you've got the actual mass as well, stopping you, or the force required with the mass. So that would be, so the inertia, I'll write it in as, well, inertial is resistive force, resistance, plus the weight. So if I add them together, I've got it's these two basically. That gives me, so what we got? 144, 145, 33 plus 384, 38.99 equals 182, 584. Some big numbers. Not surprising because it weighs 10 tons, so it's not surprising. 182, 584.32 newtons. Okay. I'm going to leave everything in these bigger numbers for now, rather than rounding them into kilonewtons. So F, find the tractive effort. So this is the force, this is the effort that's required to pull it up the slope. So it's pulling it up, and what we've got there is, so that force, the force required is, we're on F, is going to equal the effort minus the resistance. So So this effort that's pulling it up minus the forces stopping it, the tractive resistance. Don't know what's that to put it. Let's call it inertia. Yeah, the inertia one. That's it. That will do. That gives me. And remember that F equals ma. So in other words, I've got ma equals E minus Ri. Starting to run out of room. So that, if I rearrange that into that will give me, when I get my head together, so if I take the resistance Ri, this figure here, to the left hand side, I'll just do it over here. I will have E will equal M times A times plus I, which is, so the effort will equal mass, which is our 20 times 10 to the 3 times acceleration 0.5 plus this
So the
number.
minus 3, is it?
Pardon?
Just normal 3.
Power 3, yeah, 3, because it's mega. Well, it's yeah, it's mega kilograms. Where was I? So this number 182,584.32. So the answer to that, the effort is 192,584.32 newtons, which is obviously or 192.58 kilonewtons. So that's F, and then we've just got one last bit to do, G. It's a bit more work, a little bit more work for G. I'll leave that on. I'm going to rub this bit off, if that's okay. Work here. I hope you can follow everything there. So the work done, the power that's needed, that's the work done. We need the power. Find the power required to overcome these resistances.
Is that why you divide it by the time and not power?
Yes.
So,
Yeah. So our standard formula is the work done, not word done. Work done divided by time. Okay, so that's one of the standard formulas. So I need to know how long it all took to get from 0 to 5 meters per second. So I've got to use one of the other so-called Servat formulas, and the one I'm going to use, because it's easiest, is this one. So V equals, just double check myself, U plus AT, and then rearrange in case to get T. So that leads to U is 0, so if I took this to this side, V might have, let's show it, V minus U, and then divide by the T would give me A. But of course, U is 0, so it's just going to be the 5 divided by, sorry, I've done this the wrong way around. T will give me A, it's A we're looking for. So, very straightforward. It's going to be V is 5, and I've done it again. It's bad enough to make a mistake once, but do the same mistake twice is just unforgivable. Will give us T. So that's going to be 5 divided by 0.5 will equal 10. So it's 10 seconds. The whole operation took 10 seconds. So that's quite easy then.
U 0.
Yeah, P.
Because that's initial velocity.
Right.
and it started at standstill. So the initial velocity was 0. So that's convenient for the maths. So power is work done by time. So it's going to be P equals that big number over there. I'll go with the full version. 192,584.32 divided by 10. And if I can just squeeze that in, just about, I'm going to put a dog leg in here. So that will give me obviously 19258.432 watts. Very messy squeezed in watts, or 19.258, so on, kilowatts. Kilowatts. Okay with that? So not too bad.